This conference will now be recorded.
Yeah, good afternoon, everyone. I welcome you for this layout demo session. So we'll be start the layout demo session right now. So if I'm audible, not audible, if you're not able to see my screen, please I request you to put a message in the chat box, or you can unmute your microphone. You can please talk to me. Okay. Any questions from your side also? You please unmute your microphone. You can ask me. Okay. Let me start the demo session. So I'll be prefer to write the things. Okay, I'll be not using any PPT or any typing pads. I'll be just writing down. Is it fine? Okay. So let us begin with the agenda of this demo session. The agenda of this demo session. First, let me talk about the course details and the course duration. We'll be talking about course details, like what are the modes we have, and uh, what course you will be beginning what course you will be start, and advance what course, and then we'll discuss about the tool access and then mode of training. Those details we'll talk in the course details, and then we'll start discussing about the ASIC analog IC, means analog integrated circuit, ASIC flow, means application specific integrated flow. We'll be talking about this, and here we'll be understanding that what is the role of the layout engineer. So role of custom layout engineer, custom layout engineer. We'll understand the flow. Okay, and then we'll be discussing about what are the tools we are using in this course. Okay, what are the tools used in the course, and then I'll be demonstrating you demonstration of inverter. In this demonstration, I prefer to do inverter from pre-layout simulation to the post-layout simulation. Pre-layout simulation to the post-layout simulation. So in between, any questions from your side, you can please unmute your microphone. You can ask me. Okay. So coming to this course details, the course is generally we have two types. One is basics, and then advanced course, basic course and advanced course. Basic course and then advanced course. Advanced course. So in the basic course, generally you will be going through digital part, advanced digital system design, and then you will be going through the Linux course, and you will be going through scripting language. So the scripting language for as a backend engineer, layout engineer will be teaching you tool command language, TCL. Okay, and coming to the advanced courses, we'll be giving the, yeah. So one more thing, in the basic course, we'll be also covering the CMOS course, CMOS course, and then coming to the advanced course, we'll be discussing about the little bit about network analysis to crack the interviews. Few network concepts we'll be discussing, and then we'll be discussing about the layout part. Advanced layout. So in the advanced layout, we'll be discussing about LDs, means layout dependent effects. Some of the layout dependent effects are like we'll be talking about well proximity effect, LOD effect, antenna effect, latcher problem, etc. So we'll be dealing with the in the layout dependent effects, and we'll be dealing with some of the digital means standard cells design, layout of standard cells. Standard cells means standard cells is nothing but gates. So layouts of the gates, and then some analog blocks, uh, like current mirror circuits, differential pair circuits, level shifters, Smith trigger, phase detector circuits, so voltage control oscillator circuits, okay, charge pump, so etc. Circuits will be discussing in analog block design as a layout. We'll be teaching you how to draw the layout for all these circuits, and also we'll be touching AMS, means analog mixed mode signal circuits, signal circuits. So like we'll be dealing with the phase lock loops, how to draw the layout to the phase lock loops, and some converters like analog to digital converters, digital to analog converters. So we'll be dealing with this. Also, we'll be dealing some part of I/O input output circuits design, and we're dealing with some memory circuit designs, drawing the layout to the memory circuit designs, and then we'll see a few radio frequency circuits, RF circuits. So these are the topics we'll be covering in the analog. Okay, and then also we'll talk about some reliability analysis. Reliability analysis. So these are the main topics we'll be covering in the advanced part of the left in the advanced course. Okay. Now coming to the duration, the basic course generally it will happen with the 2 months. The 2 months you will be going through the advanced digital system design part, where it will covers both the combinational circuit design and then sequential circuit designs. Sequential circuit designs. The Linux part, they will be teaching you for Linux platform operating systems. They'll be teaching you that how to work with CLI approach, command line interface approach, and how to work with the Linux with the graphical user interface approach. And then they'll be teaching you tool command language. They'll be teaching you data types of the TCL, control structure of the TCL, file handling of the TCL, how to write the regular expressions, the data structures like how you can define the list arrays, strings, dictionaries. So they will be teaching you in the tool command language, and then we'll be before coming to the advanced part, they'll be teaching you the CMOS course, the CMOS complete CMOS fundamentals, CMOS working operation, MOSFET working operation, BJTs, semiconductors, bipolar transistors, BJTs, and working operation of the MOSFET. and second order effect of the CMOS. So those topics will be covering in the CMOS course. And coming to the advanced we'll talk about some network theories, and we'll understand how to calculate the resistor, then voltage, current of some circuits. So those things we'll discuss about here, like Kirchhoff law, few fundamentals about the network concepts we'll be discussing the network analysis, and then we'll jump to advanced layout course. The advanced layout course mainly will be discussing about how to draw the layout, techniques of drawing the layouts, and what is the matching techniques. So here we'll be talking about what is the symmetry layout and matching technique, correct? So what is ordering, use of the ordering, what is the use of the dummy cells, correct? So how you can reduce the process variation by adapting the layout dependent effects. The layout dependent effects will be talking about well proximity, LOD effects, antenna effects, latch up, and etc. Topics we'll be discussing, and then we'll be start discussing that how you can draw the layouts for uh, some of the standard cells means gates. Gates includes all your gates like and or not, and then universal gates. How to draw the layout for the universal gates? Okay, and then some applications gates like XR and XNOR gates. Using this, how you can design the circuit, combinational logic circuit and sequential logic circuit. So where we'll understand how to draw the layout for some of the circuits like multiplexers, muxes, means MSI circuit, medium scale integrated circuits, and we'll be discussing about order circuits like half order, full order design. Okay, order circuits, drawing the layouts, and draw the layout for so this covers in the combinational, okay, combinational circuit design, orders, multiplexers, and then transmission gates. And we'll be also dealing with some sequential circuits also. How to draw the layout for the sequential circuits like latches, memory storage device. One bit memory storage element is latches, and we'll understand that how to draw the layout for the flip flops. So then using flip flop, how you can design the counter circuits, like designing of the counters, frequency divider circuits. So that we will be discussing in the sequential part. We'll understand how to draw, how to plan to draw the layout for the standard cells. And then once you design the standard cells, then we'll understand how to draw the layout for the combinational logic circuit. So layouts for the sequential logic circuits. Eventually we start understanding, after this we'll start understanding developing a layout for or drawing the layout for the analog blocks, like how to design the uh, op-amp circuits. Op-amp consists of current mirror, differential pairs. How you can plan to draw the layout for the current mirror. How you can taking care about the process variation by adopting the matching techniques like interdigitization matching techniques, common centered matching techniques. So how you can plan to draw the layout for single stage op-amp, dual stage op-amp, some op-amp topology. So those things we will be discussing in the analog blocks design. So after designing the analog blocks, we can go for the analog mixed mode signals. Like we'll understand how to build a means drawing the layout for PLL, abstract level of drawing the PLL block, then some converters, digital to analog converter and analog to digital. So then we'll see that uh, input output pads, circuits, memory circuits, some RF circuits. So these are the course details. What we'll be covering in this 2 months. This will takes 2 months. The basic course will takes 2 months. An advanced course, including lab, will takes the 4 months course. It is. This is what the duration. This is the duration of the course. So after completion of this course, we'll be making you to attend the mock interview. The mock interview course is satisfactory. We'll putting into job support group where we can start supporting the job. Okay. So this is about the details about the course topics we'll be covering. And then if you're coming to the mode of the course, mode of course of the course. One is offline, one is online course, one is e-learning course. The e-learning course will put the recommendations. Parents to go through the recorded sessions. Any questions are there? So we'll be creating the WhatsApp group. The WhatsApp group mentor and trainer will be there. The weekends will be supporting for the weekends will be supporting for e-learning courses, e-learning students. Okay. So another one is this I can call this a weekday batch. Weekdays batches we have both online and offline. And then weekend batches also. Weekend batches both offline and online. So weekdays batch means 12:30 a.m. Sometimes in the afternoon also it will happen. Afternoon it is 2:30 p.m. to 5:30 p.m. So weekends means sessions will happen at Saturday and Sunday. Saturday and Sunday, like 9:30 a.m. to 12:30 p.m. Theory session will happen. Then after that, 2:30 p.m. to 5:30 p.m. Lab session will happen. This is the theory session, and this is the lab session. So these are modes of course. Three modes: weekdays, weekends, and then e-learning. Okay. So these are mode of courses. So this is little idea about the course details. Any questions from here? You can you can ask me, online students. Online, anybody, any questions here? You can go ahead regarding course details. Okay, so now let us start discussing about what is the role of the custom analog layout engineer. Okay, to understand the role of the custom analog engineer, first we should understand the analog integrated circuit ASIC flow. ASIC flow means what? Application specific integrated circuits. The examples for the ASIC flows like your mobile chips. Your mobile chip work as a mobile chip only. This mobile chip is not working as a TV chip. Correct. These application oriented chips, ASIC flow. Okay. If you look at the steps, what are the steps for the analog IC ASIC flow? The first step is nothing but I can call stages or steps. The first step is nothing but specification. First step is nothing but specification, and the second step is nothing but architecture, architecture entry, and next step is nothing but schematic entry, schematic entry, and the next step is nothing but pre-layout simulation. We can call pre-simulation, pre-layout simulation. The next step is nothing but draw the layout to the schematic layout drawing. The next step is nothing but what is the next step? First layout simulation, and then so once you do the first layout where you are matching the pre-layout simulation to the first layout simulation, So then you can go for the reliability checks. So then it will go to the tape out. So these are the steps for analog integrated ASIC chip design. Specification to architecture to the schematic entry to the what? Post layout simulation, sorry, pre-layout simulation, pre-layout to the what? Layout drawing. So after drawing the layout, yeah, so there is one more step here. After drawing the layout, you can do physical verification and extraction, physical verification and extraction. Then post layout simulation. So then we'll do some reliability checks. Then tape out, or you can do GDS2 file generation. GDS2 file generation. So if you take an example of full chip, so full chip is not completely made up of digital circuits, right? You made digital circuit for memory storage. Some digital circuits will be there. Okay, give me the moment. Yeah, if you look at the chip, full chip, it not only consists of digital ICs, integrated circuits. It is also having what? Some analog circuits. What analog circuits are like? You need a frequency generator circuits like PLL blocks, correct? PLL blocks are required. Means analog mix and mode signal circuits. So you need a EMS circuits like DAC circuits, analog to digital converter. So digital to analog converter circuits. Okay. So in this course, we'll be understanding that how you can draw the layout for the analog blocks and then analog mixed mode blocks and also some standard cells. Okay. So if you look at the specification, if you look at this entire ASIC flow design, uh, what means that specification here? Suppose I want to design a integrated circuit, how I can start working with designing the integrated circuits? What is mean by the specification step is? What is specification? Yes, online students, anybody? Can you please unmute your microphone? You can please answer. So suppose I want to design a any integrated chip. Okay. First, I want to see that at what frequency my chip should work. Correct. How much power my chip should will take. How much power I should my chip should take. How much bandwidth. Okay. All this will be specifying in the what at the specification stage. So if I want to design any integrated chip, it may be digital integrated or analog integrated circuit. I should specify the what constraints, some constraints. What constraints is like power constraints? So power constraints, correct? Specify the power constraints, correct? And then you can specify the frequency, at what frequency your chip should work, correct? And then you can specify the bandwidth requirement, correct? Bandwidth requirement, area constraints will be done in the what stage is nothing but specification stage. So after a specification, then we can go for what? Architecture. In the architecture, we'll decide that what are the blocks is required. So whether you need a CPU block, you need a memory block, correct? Whether you need a, some analog blocks like you need a PLL block, whether you need a input output pads block, whether you need any RF circuits block, whether you need a like circuits like frequency generator circuits or converter circuits. At the architecture level, we'll decide that what blocks are required to make a full chip. Make a full chip. So architecture will be deciding that what blocks are required to get the full chip. So the ASIC flow for the digital circuit is different. ASIC flow for the analog integrated circuit is different. In the digital integrated circuits, we'll not start with the schematic entry. We'll write the RTL code. So let me briefly go through the digital integrated ASIC flow. Then we'll come back to the analog integrated ASIC flow. If you look at the digital integrated ASIC flow, the digital integrated ASIC flow will start from the what? Same specification. The block, we'll see that what is a power constraint, what is the area constraint, and what frequency we should work. So that will be specified. After specification, we'll start with the architecture. What blocks are required to design the full chip, make a chip. Okay. And then from this, we'll start working with what? For the digital in circuits, we'll be start working with the writing the what? RTL code. So RTL is nothing but register transfer logic level. RTL code means register transfer by using what languages is nothing but hardware description languages. Hardware description languages like what are description languages like Verilog and VHDL. Very high speed hardware description language is nothing but VHDL and Verilog code. Using Verilog, so we'll be defining the behavior of the digital circuit. It is a combination of the sequential circuit by using different level of abstractions. Different level of abstractions. Like abstractions, like you know that the different level of abstraction is what? Transistor level means switch level abstraction means at the transistor level abstraction, and then gate level abstraction, then data flow abstraction, then behavioral abstraction. So most of the analog means sorry, most of the digital circuits like combination sequential circuit will be represented in the behavioral abstraction. So this high level of abstraction. So where you can use control structure to representing the behavior of the digital circuits. Okay. So using language like Verilog and VHDL, we'll write the RTL code. So means we are representing the behavior of the combinational sequential circuit through what? Programming. Okay, after architecture say that I want to so and so block. So for the block, we'll start writing the RTL code. Once you write the RTL code, we'll do the verification that we call this as functional verification. Functional verification. So by using softwares like languages like you can use a system Verilog, system Verilog, and universal verification methodology. Languages are used to do the functional verification of the RTL code. After functional verification, we'll do RTL integration. RTL integration. RTL integration means you're combining all the RTL code into the single code. Okay. So where you can see if any clocks are crossing, we'll do clock domain crossing. We call that is a CDC. Then integration will be using linked, linked and CDC. We'll do in the RTL integration stage. After RTL integration, we'll do DFT. We'll do DFT means design for testability. So in the DFT, they will be adding some additional logic to check the chip after fabricating. They're adding some additional logic to the existing RTL code to verify the uh, chip before and after fabrication. After fabrication, we'll be using the DFT, design for testability. So after DFT, this is going to the physical design. This go to the physical design. The physical design will be doing partitioning and floor plan. The floor plan will do core area, die area creation. Let me not go much detail about this floor plan. We'll do floor plan. Okay. Then we'll do placement of the cells. We'll do CTS, clock tree synthesis. We'll do routing. We'll do routing. We'll do sign off stage. Sign off stage. So after physical verification, they will also do physical design. They'll also do physical verification. Physical verification. So after done through sign off stage with the power verification and the timing closure verification, like physical verification like DRC and LVS verification. So then they will go to the what generation of GDS2 file. It's a GDS takeout stage. GDS2 file. So this file is given to the fab. Fab does not understand that directly if you give RTL code, RTL code does not understand with the fab integrated circuit manufacturer does not understand any RTL code. So what information you should give to the fab is nothing but you should give the GDS2 file. What is a GDS2 means? It is a graphical data stream. GDS2 is nothing but graphical data stream information interchange. Information interchange. So what this file contains is nothing but this is a compiled file format. This is a compiled data format. Data format. So this consists of the layout geometrical shapes data in the binary format. Okay, that means we call that is a compiled format. Compiled format means all the geometrical shapes of your layout. That layout information is available in the binary format. That should be understand the fab. Fab will understand the GDS2 file. Then it will make a what integrated chip. Make a IC integrated chip. So this is the flow of what the flow of digital IC ASIC flow. Okay. Here in the physical design, they'll be using some. They'll be using the standard cells. So they'll be using some IPs we call macros, soft macros and hard macros. They'll be using in the physical design. So IPs like analog IPs will be there. Memory related IPs are there. So those macros are for those macros and standard cells. Layout is done by the layout engineer. Okay. If you look at this for the complete digital IC integrated circuits, so this is done at the experience with 20, 30 years of experience peoples. They will do the specification for any integrated circuit. like what is a power constraint, what is area constraint, how much frequency the chip should work. All this will be done by the experienced engineers. They will do specification and architecture level design, and this is nothing but your complete front end. If you look at the digital integrated circuit, this is a front end. This is a front end stage. And DFT will comes at a front end and back end also before doing the gate level netlist. And then after doing the gate level netlist also, the DFT people will come into picture. Okay. So this you can also consider is completely, it is a back end for digital IC integrated circuit. So in the physical design, they will be using some standard cells. They'll be using some IPs, means intellectual properties blocks, IP blocks. For all these standard cells and IP blocks, so layout, design and layout is done by the analog engineers. So layout engineer will draw the layouts to the standard cells that is given to the physical design engineer. So what are the cells he's using? You will be using this those layouts in the design. Some analog IPs like IPs blocks like PLL is a IPs, intellectual property, ADC, and then DAC, and some memory or the IP blocks. So for all this, the layout is done by the layout engineer. Okay. So this is just a brief about the digital IC application specific integrated flow. Okay. You can see here you need a language to representing the behavior of the what digital circuits. What language is? You need a hardware description language like Verilog and VHDL will be preferred. So where you are representing the behavior of the what digital circuit through these languages. So after writing the behavior of the circuits to languages using any level of abstraction, we need to do verification. We need to develop the test bench and verify the behavior of the combinational or a sequential circuit. So we'll do functional verification or digital verification using system Verilog and UM. And then after that we'll do RTL integration, like we'll do linked and CDC. So then DFT, after DFT, physical design. So once physical design is done, we can go for the what GDS to generation. So these are what a flow for the digital integrated circuits. Now coming to the analog integrated circuits. So suppose I want to build any PLL block. Suppose I want to build any operational amplifier that will be used in the charge pump circuits. We don't have specifically to representing the behavior of the op-amp using any hardware description language. We don't have any languages. So where we need to design, we should design by considering the transistors, design the what schematic. Okay. So these are the steps here also. First to do the specification, architecture, then start the what schematic entry. So let's example. First, I'll start with a schematic entry. Let us take an inverter. Inverter. So, design engineer will design the inverter. What is the inverter function? Is nothing but if I apply the input as 1, output is 0, correct? If input is 0, output is what? 1. First, designer will design using, suppose if I'm designing this using CMOS 28 nanometer technology. What is 28 nanometer technology means? The spacing between the source and the drain. The length of the source and drain is 28 nanometer. Okay, you may heard about different nanometer, 90 nanometer, 180 nanometer, correct? 28 nanometer, 16 nanometer, 14 nanometer, 7 nanometer, 5 nanometer.
Can you, hello,
Hmm.
sir? Hello?
Yes, yes,
Can
yes.
you
Hello.
repeat the nanometer technology? Because this time our internet connection was not good. I cannot hear you.
Okay.
What is the nanometer technology? Can you repeat?
Nanometer. Yeah, nanometer technology is nothing but suppose if I draw like NMOS, the distance between source and the drain. If I draw the cross-sectional view of the inverse, how the cross-sectional view of the inverse? The cross-sectional of the cross-sectional view of the inverse is, first we'll take this PVL process, or there is a uh, BiCMOS process. If I'm talking about NVL process, let me draw the cross-sectional view of the inverter directly so that you can understand what is a nanometer is. If I draw the cross-sectional view of the CMOS, cross-sectional view of the CMOS, first we'll take the what? Substrate. This is a P substrate. This is P substrate. In the P substrate, this is the housing by what? NVL. I'm doing NVL process. This is a NVL. The NVL will form the what? PMOS. The PMOS will housing with what? A strong P plus region. So this is a strong P plus region. And then the P substrate will form the NMOS. This is a N plus region, and this is the N plus region. So this is a NVL. In the NVL will form the what? PMOS. So this is a PMOS, and this is a NMOS. Okay. So how you can form the channel between the source and the drain is, first layer is nothing but what? This is oxide layer, and top of this oxide layer will form the what? Polysilicon. This is what the polysilicon. What is the channel length is nothing but the distance from the source to the drain. If you look at the structure of PMOS or NMOS, generally it is a four terminal device. What are the four terminal devices are like? One is gate terminal. So gate terminal is responsible to form the channel between the source and the drain. Okay, and then source terminal and drain terminal. If I talk about this is a inverter, so this is a source. I can call this a drain. The source is connected some potential. Okay, again this is NMOS. This is a oxide layer. This is the gate. Generally, lower technology node, the gate is made up of polysilicon. Higher technology node, the gate material is also made up of metal layers. Okay, so this is a gate, and this is a source, and this is the drain. What is the channel length is nothing but the distance between what? The source and the drain. This is nothing but channel length. The distance from source to the drain is nothing but a channel length. So here, if you look at the inverter, VDD is applying to the what? Source, and drain will be shorted, connecting to drain and drain, and this source is connecting to the what? VSS ground, and this gate and gate will be connected. This gate and this gate is connected. This is connecting to the input, and this is connecting to the output. If I'm applying input is equal to 0, in that case my PMOS is on, NMOS is what? Off. NMOS is off, where VDD is connecting to the what? Vout. So if I'm working with VDD off, say for example I'm working with 1 volts, I'll get output is equal to what? 1 volts. In this case, the PMOS is on. Okay. If input is 1, Vin is equal to 1, this PMOS is off, and this NMOS is on. NMOS is on. Now it is acting as a path. There is a channel between source and drain. So this Vout is connecting to the what? VSS. Now this is discharging path. It is acting as a discharging path. When PMOS is 1, it is acting as charging to the what? VDD. and then NMOS is on. So VDD is discharging to the what? VSS. If I write the schematic to this is what your PMOS, symbol of PMOS, and this is a symbol of what? NMOS. Correct. So is source, this is a drain, and this is a gate. This is a drain. This is a source. This is a gate. So where gate and gate should be shorted, both are getting shorted. This is the input, and drain shorted is nothing but output. So usually this we call it as pull-up network. PMOS is at the pull-up network, and this line we call it as a demarcation line. Above demarcation line is nothing but pull-up PMOS. Below demarcation line is nothing but what? NMOS. So if input is 0, PMOS is on, output is charging to the VDD, and input is 1, this NMOS is on, so that output is discharging to the what? VSS. So that it is acting as an what? Inverter. If I apply the input is 1, output is 0. If input is 0, output is what? Did you understand? Okay. What is the confusion? Yeah, let me draw. Okay, let me redraw this circuit again. So this is what the demarcation line. Demarcation line. Above demarcation line is nothing but PMOS. Below demarcation line is nothing but what? It is NMOS. Okay. So this is a PMOS. This is a NMOS. So this we call pull-up network, PWN. So this we call it as a pull-down network, PDN. Pull-up network and pulling down. So this line we call it as the demarcation line. Okay, to design the inverter using CMOS, pull-down network is NMOS. So in this case, gate and gate will be shorted. This is connecting to the input, and this is a drain terminal. Let me represent a source, drain, and the gate terminal. Again, this is a drain, source, gate terminal. Gate and gate is shorted. That is connecting to the input. So drain and drain is connected. So this is connecting to the what? Output. So this source is connecting to VDD. So this source is connecting to what? VSS. If input is 0, PMOS is on. If input is 1, NMOS is on. If input is 0, Vout is charging to the VDD through this. This is acting as an on, so that Vout is charging to the VDD. And when it is 1, this is off and this is on. Did you understand? So this is what the schematic entry. This is a schematic entry. So after schematic entry, what I need to do? What is the next step is nothing but pre-layout simulation. The next step is nothing but pre-layout simulation. Pre-layout simulation. So in the pre-layout simulation, we'll do various analysis. We'll do DC operating point analysis, AC operating point analysis, and then DC sweeping analysis. All the analysis we'll do at the way in the pre-layout simulation. Means, suppose I want to give the input to this inverter as an square wave with the rise time, fall time of 0 picosecond or 0.5 picosecond. So this is the input I'm applying to my inverter. Okay. So I want to do some transient analysis. Transient analysis means input and output analysis. If I apply this square wave as input to this with some frequency, okay, or with some time period, from the time period you can also calculate the frequency, right? Time period, and what is the R period and what is the time period. So that is completely one clock period. If I apply this input to this inverter, correct? So what I'm expecting is, if it is 1, output is low. If input is 0, output is 1. This is what the output I'm expecting at the what? Output of the inverter. Did you understand? So this is what the pre-layout simulation verify the behavior of the circuit. And if you're designing any analog circuit, get the DC operating points to understand that transistor in what region of operation, like it is in saturation region, linear region, cutoff region, or subthreshold region. We'll do DC operating analysis. So and then if you are designing any analog circuit, if where you want to plot the frequency versus the gain in dBs, then you can do what? AC analysis. You can do various analysis at the what? Pre-layout simulation stage. So once you verify the behavior of this circuit by doing all this analysis like you can do transient analysis, do DC analysis, do AC analysis, then DC sweeping analysis. Okay, other analysis you can do in the pre-layout simulation. In the pre-layout simulation. Okay. So we'll do all this analysis, verify the behavior of the circuit. So once you verify this schematic is giving to the layout engineer. Okay, this is a job of, so from here to here, this is a job of design engineer. So this you can call it as what? Design engineer. Suppose I'll ask my designer, I want a in my integrated chip, I want 40 dB of gain. I want a circuit which should amplify the signal. If I give 1 millivolt signal, I want to amplify with the 40 dB of gain, where I want to boost my input signal. If I ask my design engineer, he is going to design the circuit. Okay, by keeping all these parameters, considering all these parameters, the design engineer will design the schematic. But so and so W by L ratio of the transistors means aspect ratio of the transistors. Okay, so what ID current is required for this transistor, what ID current is required, okay, at what input voltage VGS I should work. Okay, so based on this, design engineer will design the circuit. This circuit is giving to the what? Layout engineer. So where layout engineer will draw the what? The next stage of this is nothing but after layout simulation we'll do what? Layout drawing. Draw the layout. Draw the layout. So first to draw the layout, what is of course layout? What is a layout? Of course, what is a layout engineer? What is the job of the layout engineer? Yes, online students. Anybody? What is the role of the layout engineer? Custom layout engineer, or you may talk about full chip engineer, custom layout engineer, semi-custom engineer. What, of course, what is mean by layout? So layout is nothing but you're telling the fab, you're telling the fab that these are the mask layers you need to form. So what is layout is nothing but this is nothing but mask information. Layout is nothing but a mask information. So that details is given to the what? The mask information is given to the what? Fab. You are saying that fab man, this is what the layers you need to grow to design so and so integrated circuit. So that information is given by what? Layout engineer. So to draw the layout, first you will be understanding how to draw the sticker diagram. Sticker diagram. Okay. So layout is also, you can call it as stick diagram with some standard dimension. It is all about the mask information. In general way, if you talk about what is a layout, is nothing but this is what? Sticker diagram and place with what? Some dimension. So dimension means 28 nanometer fab will gives the some DRC rules. When you are drawing any layout, how much distance you should maintain. Layer to layer means metal to metal distance. Okay, what is the area of the metal you should use, and You should see that how much area you should use for the vias. All this information is given by the foundry. So in general way, what is a layout is nothing but it is a stick diagram plus what? Dimension. You don't understand. So to draw the layout, first you should understand how to draw the stick diagram. So if you look at the stick diagram of inverter, you will be having what? VDD rail. This is what the VDD rail. This is a VDD, and this is what? VSSI. This is what? Demarcation line. Above demarcation line is nothing but PMOS, and this pull down network is nothing but PMOS. This is a pull up network. This is a pull down network is a NMOS. If you look at the inverter, gate and gate will be shorted, correct? This gate and this gate. If I consider this is a gate terminal, let me write this is a gate terminal. This is source and this is the drain. Transistors are representing like a plus symbol here. So this is a gate and this is source and this is the drain. So here gate and gate will be shorted. This gate and this gate will be shorted, and this is connecting to the input. This is connecting to the input, and source is connecting to the what? VDD. PMOS source is connecting to VDD. NMOS source is connecting to the what? VSS. And this drain will be shorted. This is connecting to the out. This is connecting to the out. Okay. So for this, you should draw the layout. If you look at the layout, it is very difficult for me to layout here. So what I'll do, I'll just copy from the tool. So whatever the layout we have designed, let me copy and I'll explain from that. So this is a layout of inverter. This is using nanometer or nanometer PDK. We are using is nothing but 28 nanometer technology. It is the 28 nanometer technology. The channel length we are using is how much is 28 nm. Okay. So this is what you are completely PMOS. What is the background? What you can see is nothing but this is a P substrate. The black color is nothing but P substrate. The P substrate we are housing with the what? So this is a N-well layer. The N-well layer we are growing the what? Oxide. In the diffusion oxide it is. The yellow color what you can see is nothing but diffusion layer, and this is nothing but what you can see red color is nothing but so this is a gate. It's polysilicon material. Polysilicon, where this is what your source terminal, and this is nothing but what source region, and this is what drain region. Now this is what complete PMOS. Above is PMOS. This is what your VDD. This is a VDD, and coming to this pull down network, this is what VSS, and you can see what is the red color. You can see is nothing but this is a P implant layer. P implant layer to form the PMOS, and this is nothing but this is what your cross sectional view. If you look at the cross sectional view, this substrate is housing by what? N-well. This N-well is housing by what? P implant layer. Where in the P implant layer, where you are forming the source and the drain, and then gate. This is what layout will gives the what top view. So this is a top view of the layout. Layout one gives you like three-dimensional view. This gives the what? top view. This information you are giving to the fab in terms of GDS2. So fab will understand that what are the masking layers we need to grow. That information you should give in terms of what? GDS2 file. Correct. For this schematic, you should draw the what? Layout. If you see the layout, this is what the PMOS and this is what? NMOS. So this is N implant. This is N implant. Again, this is gate terminal. So this is source terminal. This is what? Drain terminal. So in the lower technology node, we'll be using some dummy gates. We call this nothing but dummy gates. So this is used to reduce the etching process. Etching effects can be reduced by putting the what? Dummy cells, dummy gates. Dummy gates is like does not carry any current or voltage. It will not drive any current or voltage. So this is used to reduce some layout dependent effects. To reduce the etching during the etching process. Uh, See, when you are fabricating this is what all the shapes what you are writing is nothing but ideal shape. All these are in ideal shape, correct? After fabrication, there are some systematic variations will happen. The fabrications like etching, doping, ion implementation, and oxide diffusion, you won't exactly get the same ideal shape. You will be getting some non-ideal shapes. Suppose I'm fabricating this poly, I'm not getting exactly like a square shape like this. I'll be getting poly like this, some non-ideal shape because of process variations, some systematic process variation like etching process, then ion implementation, doping process, oxide variations, oxide thickness variations. You won't get the ideal shape, you will get the non-ideal shape that is happening due to the process variation. You understand? So where you should layout engineer, where you should consider to reduce the process variation. You can't avoid completely 100%, but you can try to minimize it. So to minimize that, you should follow the various layout dependent techniques. Okay. So this is what the information you're giving to the fab that to suppose I want to integrate the inverter. I want to get a silicon of this information giving to the, like this much of geometry of poly you should form, this much of source by using this metals are using generally aluminum materials are used to fabricating the source and drain regions, huh? This much of metal you should fabricate. Those information is given to the fab. Okay, so I can call this layout is nothing but, so this is stick diagram, right? Exactly stick diagram you have designed here. This stick diagram with what? Some dimensions. What dimension means? Suppose if I'm using poly to the poly, what is the distance between poly to the poly I should use? So that we call DRC rules. That we call it design rule checks. So this is given by the foundry. Suppose I'm using 20 nanometer cell. The distance between source and drain is 20 nanometer. DRC will tells foundry will tells that DRC rules. How much distance you should use one poly to the another poly distance. Okay, what is the distance between metal to metal? This I'm using M1 metal, here also M1 metal. How much distance I should use metal to metal? How much minimum area of NVEL I should use? Okay, how much P implant area I should use? So all these are design rules will be given by the foundry that we call DRC checks. So once you draw the layout, after drawing the layout you will do the design rules checks. So why I should do the design rule checks here? What is the role of the design rule checks? That is what I'm giving this space. Why I should give this much of space? Why I should follow these DRC rules? So these DRC rules are following to fabricating the correct integrated chip in the particular technology node. If you're not following this distance, you may getting the chip, the fabricated chip which is defected. So if I want to make a high yield integrated chip, 28 nanometer foundry will tell all the DRC rules where I should follow all the DRC rules to fabricate the correct integrated chip. So where we should follow the what? DRC rules. Correct. So I can call simply layout is nothing but this is stick diagram, right? This is PMOS, this is NMOS, how the source is connecting to VDD, gate and gate is connected, this source is connecting connecting to the VSS. This drain is connected, and this is connecting to the output. You do understand? Or else layout is nothing but a top view. It gives the top view information. Yes or no? This is not a cross sectional view. If you look at this cross sectional view or a three-dimensional view, if you look from the top, what you can look from the top? There is a gate. There below this there is a oxide. Then there is a source region, drain region. There is a end well. There is a what? P substrate. If you look from the what? Top. If you look from the top, correct? So layout gives the what? It gives the top level, top view of the what? Your not a state diagram, a stick diagram. The top view information it will give. Means all these mask layers. These are the mask layers for the transistor. For all the mask layers, you can view into the what? Top view. So from this, you can generate a GDS that is given to the fab to fabricating the integrated chip. If you look at the steps, first we'll start from the specification, correct? Then architecture. This is a digital IC. Sorry. First start with the specification architecture. Then start with the what? Schematic entry. And then start with the what? Pre-layout simulation. So in the pre-layout simulation, you are checking the behavior of the what? Circuit. But coming to the digital integrated circuits, we'll not start with the schematic entry. We'll write the behavior of the circuit using what? HDL means hardware description languages. By using very long or very high speed description language like VHDL, we'll write the behavior of the digital circuit through hardware description language that we call RTL, register transistor level logic. The register transistor level logic it is RTL. So after writing the RTL, what we'll do? We'll do verification. But in the analog integrated circuit, we'll start with a schematic. There is no separate tool or any languages to uh, design any representing any behavior of the circuit. So manually you should design. You should verify what is the WL ratio of all the transistors is required, and we'll design the schematic. Okay. Once you design the schematic, we'll do what? Pre-layout simulation. Here we call it as what? Functional verification. We'll do functional verification means verifying the behavior of the RTL code. Okay, register. It is not a register transistor logic. It should be register transfer level code. RTL means register transfer level code. Okay, here we'll do a pre-layout simulation. We'll for circuits we'll do various analysis. Okay, like AC analysis, DC analysis, transient analysis, DC sweeping. If you want to do FFT on some signal, you'll do FFT, DFT. All the analysis we'll do. So after doing the analysis, so this design is giving to the what? Layout. This schematic is giving to the layout. So a layout engineer will draw the what? Layout. Means mask information. What are the layers you need to grow to integrated this schematic to get this integrated of this schematic? We'll tell that these are the layers you need to use to design these circuits following the DRC rules. So DRC rules will be different for 95 nanometer, or if you are working with 90 nanometer or 28 nanometer, or working with a 14 nanometer or 7 nanometer, DRC rules will be different. So this you will get it from the what? Foundry will give this information. Foundry will give this information. From this information, you should draw the layout. So once you draw the layout, then you should do what? Physical verification like DRC, and then you should match the layout versus schematic versus layout, so that we call it as the LVS checks. So in the physical verification, we'll do DRC checks, design rule checks. We'll do LVS means you're matching with the what? Layout, a schematic, whatever the schematic you're captured, that schematic should be matching to the what? Layout. Like you should match all the devices with the length. You should match all the properties of the device. You should match all the nets connections. You should match all the ports connections. You should match all the device properties. All the device properties you should match. If your schematic and layout are matching, then LVS is clean. LVS is clean. If you are following all the DRC rules when you are drawing the layout, the DRC rules are following, then it will give the DRC is clean. So after drawing the layout and verifying DRC and LVS, that we call physical verification. So then you will do the parasitic extraction. We call extraction means what? Extraction is nothing but parasitic extraction. Parasitic extraction. What is a parasitic extraction? Is like extracting the resistance, extracting the what? Capacitance. We can also simply we call RC extractions. Because when you use any metal having some resistance, we call that is sheet resistance. How much sheet resistance? If you look at this layout of inverter, this is a M1 metal. This metal having some resistance. The resistance will be calculated unit square. Okay, and between two metals, it is forming the parasitic capacitance. You know that capacitance means what? It is a two parallel plates. One plate is connecting to what? Higher potential. Another plate is connecting to what? Lower potential. Between this parallel plate, the spacing is filled by what? Here are dielectric. Correct. Some sort of insulator metal. So if you apply the supply voltage to this, now it is charging, is storing the charges. Correct. Two plates are parallel. Between this, if this is a one metal, and this is another metal. If this is connecting to some higher potential, and this is connecting to, suppose it is connecting to the ground or VSS, foundry will fill some filled gaps. All these filled gaps will be filled by some sort of insulator material. The electric material, they will fill it. Now between these two, so there is a coupling capacitance will be formed. Now these are nothing but very similar to this one, right? Two metals are connected parallelly. In between this, there is some sort of dielectric or a hair will be there. This is acting as a capacitor. Correct. So we should extract how much capacitance is forming, how much resistance is forming. That we call it as what? Parasitic extraction. So we'll do parasitic extraction. We'll do parasitic extraction like RC extraction. Then we'll understand that how this RC will affecting the schematic. Means we should try to match the result of your schematic result should be matching with the what? uh, Post layout simulation. So after extracting the parasitics, then we'll do what? Post layout simulation. Means for this layout, whatever the inverter you are designing, drawing the layout for this layout, we'll apply the what? Inputs. Like suppose I will apply the input as what? Square wave, correct? Then I should get output as a what? Complement of this. This is a transient analysis I'm telling you. So this is what input if I apply to this layout, I'll getting this output. But this output will be varied because of capacitance and some parasitic capacitance is formed, where you should optimize the we should reduce the parasitic resistance and capacitance to match the output of what? This pre-layout simulation to the what? Post-layout simulation. Whatever the simulation you are getting from here, in the first layout simulation, this result should be matching to this. And where you should understand that how it is impacting this parasitic resistor capacitor. Suppose you are not properly drawing the layout with asymmetry layout you are drawing, where parasitics are not uniformly distributed in all the sites, where you should understand that how you can optimize the parasitics to match the result of your post layout simulation to the what? Pre-layout simulation. If both are matching, so then you can go for next stage. Go for the reliability checks, like you will do some electromigration checks, we'll do some crosstalk, we'll do some IR drop checks, we'll do shielding checks, we'll do some antenna checks. So after doing antenna checks, reliability checks, then you can go for what? Generation of GDS2 file. So this GDS2 file will be given to the what? Fab to integrate it, integrating the chip. Did you understand? So what is your role as a custom layout engineer? Your role is mainly what here? Layout part. For any schematic, you should understand that how to draw the layout. Then how to do what? Then how to check with the what DRC rules based upon which NM you are working on. Did you understand? Physical verification. Okay. And also do parasitic extraction. So this is what your job. For analog blocks, you will start drawing the layouts, and then when you are drawing the layouts, what are the techniques are available? Like op-amps will be using to reduce the process variation, where we'll be using common centroid matching techniques, where we'll be using interdistinction matching technique. How you can adopt the matching techniques to reduce the process variation for transistor, for the resistor, for the capacitor, how you can use the matching techniques. So those things will be focusing in the layout part, layout dependent effects, along with some techniques to draw the layout for analog circuits, digital circuits, then standard cells, then the standard cells. Okay. In digital circuits also we create also. In the digital circuits, we also standard cells. Standard cells. Standard cell is nothing but it is height wise. It is fixed. Okay. Height is fixed. Width will varies based upon number of inputs to the circuit. How many inputs and complexity of the circuit, width will varies, but height is fixed. Suppose you talk about 28 nanometer, the standard cell height is different. Standard height is nothing but, suppose you take this is inverter, this is a standard cell. Huh? This height will be fixed. This height will be fixed. Height is fixed based upon the number of tracks. We'll understand those things later. Tracks. So tracks is calculated based upon how many routing layers you can allow on the top of this inverter. Means this CMOS. Okay. For 28 nanometer, the number of tracks is 11 tracks. Okay. And then into pitch, we call pitch is nothing but spacing between one metal to another metal, center of one metal. Suppose if I'm drawing two metals like this, two metals, the center of this metal to center of this metal is nothing but a pitch. Using pitch, how many tracks for the 28 nanometer is nothing but 11 tracks. The pitch is for suppose if I'm talking about metal one, what is the pitch is nothing but 0.152 into 11. The height of the standard cells you will get 1.6720. The height of the standard cell is nothing but this much of micrometer height. So standard cell is nothing but a all the gates where height is fixed based upon the technology nodes. 28 nanometer is 1.67 to 40 nanometer where height is different. Height will be calculated based upon how many routing layers you can follow and based upon the power rails and then VSS rails. We'll consider few parameters to fixing the height of the standard cells. But coming to the analog is not same true where width and W by L ratio is keep changing. Okay. If height is fixed, that cells we call it as standard cells. Okay. These are the entire steps to doing the what analog integrated circuits. Analog integrated circuits. So in the reliability checks, you will do EMIR checks, means electromigration checks, some IR drop checks, and you will do crosstalk checks, and you will do shielding checks. Shielding is used to covering the sensitive metals. If any metal is carrying the sensitive signal, to reduce the crosstalk, we are going with the what shielding techniques, and you will do antenna checks. Some reliability checks will do. If this is matches, then we can go for the GDS2 generation that is given to the fab. Okay. Uh, so any questions in this regards, you can please ask me. The flow of analog integrated circuits. Like any questions from your side, can you please go ahead? Online students. If you have any sort of question also, please you can ask me. If it is a basic question or it is advanced question, anything is there from your side, I request you to unmute your microphone. You can ask me. Okay, this was the flow. Now let me discuss about what technology nodes we will be working with this course. We'll be working with two technology nodes. One is 28 nanometer PDK process design kit. Okay, so this we'll do using Synopsys tool. 28 nanometer using the Synopsys tool. Okay, the Synopsys usually will not do these two steps. This is coming from the what? Like chip top means full chip engineer will give us all the specification and architecture. He will decide, but we'll start from the what schematic entry. So from the synopsis, what are the tools we are using for various stages in the analog uh, integrated circuit is for a schematic capturing, we'll be using the tool called it as a custom compiler tool. Custom compiler tool. Okay. For doing the pre-layered simulation, generating the netlist, we'll be using tool called it as a prime view tool. We have the HSpice tool for generating the netlist in pre-layered simulation. Yes. To draw the layout, you will be using the tool called as custom compiler. Custom compiler. And to do physical verification like DRC and LVS, this DRC and LVS is done by using tool called as IC validator. IC validator tool. And to do parasitic extraction, this parasitic extraction will do using star RC2. Star RC2. And this post layout simulation, you can use the same tool called prime view, and then HSpice you can use prime view tool. And for like cross check, IR drop, EMIR, reliability checks, we'll be using the tool called it as a Red Hawk tool. Red Hawk, Red Hawk tool, and we'll generate. No. So this is for like EMR, IR checks. Hmm? You need some supported files to generating the GDS. Huh? So GDS, there is no separate tool. Once you do all these checks, this layout, all the geometrical shapes you should give in terms of what binary information to the fab. So there are certain uh, files are required. Using that files, we'll generate the GDS to stream file because basically that is a stream file. That stream file is giving to the what fab. Okay. So this is we'll do this using 28 nm PDK using Synopsys tool, and then we'll also work with the custom compiler tool also. Sorry, Cadence tool also. So why we are doing both the tool is as a market, the market most of the time the candidates they're asking to preference with the what both synopsis tool as well as the cadence tool. That is the reason that we are working with what both the tools, synopsis tool and cadence tool. So in the cadence tool for 28 nm we'll be using MOSFET. We'll be using the MOSFET. Okay. From the cadence we'll be working with 18 nanometer. 18 nanometer. This is FinFET. FinFET. It is not a planar MOSFET, it is a FinFET. So in the cadence, the tool from schematic capturing is nothing but Virtuoso tool. Virtuoso tool. And to do pre-layout simulation, the tool called it a Spectra tool, Spectra Excel tool. And to draw the layout, we'll be using the tool called as what? What is a tool? And then to do physical verification, we'll be using the tool called as Pegas tool for physical PVS verification. Means this from the synopsis. Synopsis, whatever the green color, what you can see here. So these are the tools from the what? Synopsis company. We call these EDA tools. Electronic design automation tools are used to design the analog integrated circuits or digital integrated circuits where you need EDA tools. So these are the EDA tools are used to design the analog and digital integrated circuits. So whatever you can see in the green color here, these are the tools related to what? Synopsis. Okay. And whatever I'm writing in the yellow color, these are the tools from what? Cadence. For layout also we'll do what is so. And then physical verification will use Pegas tool. PS means physical verification. And extraction, stars means parasitic extraction. This extraction will do using Quantas tool. And to do some reliability checks like IR drop, crosstalk, EMI. What is the tool we are using from the Synapse nothing but Voltas tool. This course you will be encountering with these are the tools for complete. So this I am talking about from schematic capturing to the what up to reliability checks. So these are the tools. But as a layout engineer, you will be mainly focusing on what layout using what you saw in Cadence, custom compiler using Synopsys, and you will be working with what physical verification using IC validator from the Synopsys, Pegas from the what Cadence tool. So here I'm just giving the idea that what are the tools you are going to use from static entry to the what reliability checks. So these are the tools we'll be using. So, any questions regarding that? What technology node we are working on? What are the tools we are using? Hmm? So, the tool access will be 24 bar 7. We will be guiding you that how you can connect into the server. Those steps will teach you. Through VPN, you should connect into the server. After 2 months. After 2 months, we'll give this one tool access to start kick starting with the layout part. Okay, where we'll be teaching you that how to connecting to the server and how to invoke these tools. Now you can start creating the libraries and then cells creations, then how you can draw the schematic, then layout, then how you can do parasitic extraction, then how you can do post layout simulation. Few circuits I'll be teaching you all the steps from schematic capturing to the post layout simulation. But as a layout engineer, you will be mainly focusing on how to draw the layout to the given schematic. Okay, but anyway, with the flow, we'll understand that how we can start working with the schematic entry to the what post layout simulation. So this is about the flow, how you can fabricate the analog integrated circuits. So this is the steps, starting from specification to the reliability checks. So, any questions from this slide, you can please ask me. Any other questions from your side, you can please unmute your microphone and you can ask me. Yes, online students, I am not getting proper response from the you. Can you please go ahead? Any sort of question, you can unmute and you can ask me. Whether your questions about relating to the course or training or tool or any other topics you are expecting any questions from your side, can you please go ahead? Yes, please. Hello.
Sir, can we attend other domains demo session also?
Yeah. So today morning there is a physical design demo is happened.
Okay.
I hope you have not received the link for that.
No, sir, I have not received.
Okay. So morning demo, one demo session is happened for physical design, and yesterday it is happened for the front end. Front end design demo session has happened yesterday. If you want, I think you can request. They'll be providing you the recorded sessions. You can go through the recorded sessions.
Okay, sir.
Okay. Now let me give the demonstration. Uh, how you can start working with the layout, unlike integrated circuit steps. So I'll be giving demo on inverter. We'll understand how to draw the schematic, then pre-layout simulation. So then now you can start working with the drawing the layout, and we'll do parasitic extraction. What are the tools are we are using? So that let me start now. So I'll be using synopsis tool, 28 nm cell. So this is what tool we called as custom compiler tool. Okay. I'll be once your course start, we'll be teaching you all the steps. Currently, you don't worry about how to create the cells and views, then schematic and layout. Uh, just I'll go through this. I mean, I'll be designing this. Then you can follow the steps. Okay. Any question in any steps you can ask me. Okay. So for this, we'll be using the tool called as custom compiler tool. Huh? We should create the library manager. In the library manager, where we should create our libraries. So in the libraries, where you need to create the cells and the cell views. Suppose for this one, I'll create the library. Go to the file, library. So then you can create the library. So I can create the library name like April demo session. And the technology node is here. You can select the technology node. What technology node we are working with. See this tool, we have different technology nodes like 90 nanometer technology node and then 20 nanometer technology node, where you should select the technology library. What technology library we're working with? So we are working with this Synopsys Academic Education Design PDK 28 nms. Okay, this is a PDK we are using. Let us click on to OK. So once you create the library, you can create the cell. So to create the cell, you go to the cells and right click and create the new cell. So I'll be giving the cell name as an inverter. Inverter. So this cell I will give as a schematic first. So if you look at the flow for unlock integrated circuits, first we should start from the what? Schematic entry. So create the schematic. So this we call schematic canvas. So here we are going to draw the schematic of the inverter. To draw the schematic of the inverter, so you need what? PMOS and NMOS cell, correct? I'll be using PMOS and NMOS cells. PMOS with the four terminal device and NMOS with the four terminal device. This is a PMOS and NMOS. And if you see that connection of inverter, gates and gates will be connected, correct? Drain and drain will be connected. And source of this is connecting to VDD. Source of this is connecting to what? VSS. So this is a four terminal device. Another terminal is nothing but the back gate, or we call it as a body terminal, body or a bulk. So this bulk usually connecting to the sources in PMOS and NMOS. So this bulk is connecting to the what? Source. So NMOS bulk is connecting to the source and PMOS bulk is connecting to the what? Source here. So this is output and this is what the input. So then you should do pin connections. I'll be using the pin connection. So what pin is nothing but this is the input pin. So type is input. I'll connect the input and I need an output pin. So this is in output. Sorry, output pin it is. I'll connect the output and I should connect the VDD and VSS. VDD and VSS. So this is a in output type. So this is a VDD connection and this is what? VSS connection. To draw the schematic, we'll be using tool called as a custom compiler tool. This is what the custom compiler tool. So this is what the schematic capturing of the inverter. So once you capture the inverter, so then you should do check and set. Check the current view for any violations. So here I'm checking the any rule violations is to this schematic. It is showing that no rule violations are found in the this library. Library name is nothing but April and then name of this cell is nothing but inverter schematic. Did you understand? So this is what the schematic capturing. Once you create the schematic, then you should create the symbol. So now you do the symbol creation. So where you want the pins, you can keep it and then create the symbol to this. This is what the symbol of the inverter. If you want to draw the shape of the inverter, you can use by using this or the shapes. You can create the symbol of the inverter. For this demo, let me skip that part. I'll be using this same for creating the inverter. So this I'm considering as a what? Inverter. So this symbol creation and then symbol schematic creation is done here. So after this, you should create the test bench to this. I need to verify the behavior of the what? Inverter, right? For this, I need a test bench. For creating the test bench, I'll be using the cell name as inverter TB. Inverter TB. This is inverter TB. So then create the schematic first. Create the schematic. So here you can instantiate the cell, the symbol what you have created. This is symbol of inverter. Okay. So the step one is nothing but the schematic capturing. The step two is nothing but what? Pre-layout simulation. For doing the pre-layout simulation, I should give some inputs, right? Inputs to the inverter and get the output. For that, I'll be using some sources. Let me go to the analog library. Go to the analog library. Get the sources. I'll be using vPulse. So these are vPulse I'm connecting here. Then I need a VDD. I need a VDD. VDC, sorry. Let us use VDC. Two VDCs I'm using. I'll connect the two VDCs. And I need a ground symbol. Let us use the ground. Ground. So then I need a capacitor. Capacitor as a load cap. I'll be using the capacitor. So after this, I'll do wiring. So positive of this source is connecting to the input and negative of this is connecting to the ground. I'll copy this ground, I'll connect it here. So then output is connecting to the cap and this cap one terminal is connected to the ground. I'll copy this. This is ground. Let me delete, I'll copy two. So I removed one. Okay. So then I should do wiring. So this is connecting to VDD. This is connecting to VDD. This is connecting to VSS. And this is VDD. I'm going to label. This is nothing but label for VSS. So after this, I'm going to label this by pressing L. So first I'll label VDD. Let me label the VDD. So this is labeled as VDD, this is labeled as VDD, and then label the VSS. So this is a VSS, and this is the VSS, and then also you can label input and output. So I'll label this as an input, and then output. This I'm going to label as input. This I'm going to label as a output. So now I'm going to give some design variables. So let us work with VDD as a design variable as VDD. I'll give DC voltage to this. VDC is nothing but VDD, and this DC voltage as VSS. So then I'm going to give some design variable to this. This voltage I can give this as 1 volts. This I can give as 0 volts. Let me give time delay 0. Let us give rise time is 1 pico, and fall time is 1 pico. 1 pico. Let me work with the time period of 10 nanoseconds. 10 nanoseconds. And then pulse width is half of this. I'll give the 5 nanoseconds. I'll be using pulse width of this is nothing but on pulse and off pulse, on pulse and off pulse would be half of this. I'm using 5 nanoseconds. Let me save this. You are the design variables I'm giving to this source. After doing this, you can create the sheet for this. To creating the sheet, you can add and go to the sheets, and you can add the sheets. Let me add the shell sheet size is E4 sheet. Then click on to OK. So this is what the inverter. Inverter. I'm applying some input source as a pulse. So here I'm not giving the capacitor value. Let us give capacitor value as a cap design variable. I'll give this as design variable. What are the design variable I'm working with is nothing but VDD, VSS, and then cap is the design variables. Okay. For this VPL source, I'm giving all this here. What is a high voltage, what is a low voltage, what is a rise time, fall time, pulse width, and period I'm giving here. Remaining I'm giving as an option. So this is what the test bench. Now I should do the pre-simulation to this. What is the tool we are using is prime view tool. Use the prime view. This is what the prime view tool. The step one is nothing but we should add the model files. So model file contains the cell information like power area information. We should add the model files. So where it is located is, let me see the location of this one. So this is located in home, tools, synopsis, synopsis install, and we are using the PDK. What PDK is nothing but 24 PDK, HSpice. Choose and add the model files and do typical corner analysis TD, then click on to OK. So we are done with the model file, and then we should copy the design variables. Copy from the design. These are the design variables. So let us work with VDD is 1 volts, VSS is 0 volts, and let us work with capacitor is 0.1 or 0.01 picofarad. So after adding the design variables, then you should do the analysis. What analysis I should do is, let us do the transient analysis, means input and output analysis. Do the transient analysis. Start time is 0 and stop time is, let us give 100 nanoseconds, and let us give the time step is so 10 picoseconds. Enable this, then click on to OK. This is what the analysis we are setting here. So after doing the analysis, you check the simulation options. So netlist should be created using HSpice, not from the third-party app. And then simulation engine we are using is Prime Sim Spice. Set up this option, then click on to OK. So then you can simulate this. Simulation, netlist and run. Now simulation has been started. So the simulation status you can check in the job monitor. If any errors in your simulation, it will print it is file. If there is no error, uh, it will uh, it will print here as a finish. Now this simulation has been finished now. Here to see the waveforms, what you can do, go to the outputs, you can add from the design. Now I'm going to add the waveforms, input waveform and then output waveform. Before simulation, I did not add this. Anyway, I have done with the simulation, one simulation. Now if I click on to evaluate and plot, this is what the input output evaluation. Okay. Now to ungroup this, you can go to the option like ungroup. So this is what the input. If input is 0, this is what the output. Output is 1. If input is 1, output is 0. So the transient analysis we have done for the what? Inverter. So this is step we called as what? Pre-simulation steps. Now we are verifying the behavior of the what? Inverter. Using prime sim I'm using. Okay. So after doing this pre-simulation, the next step is draw the layout to the inverter. Okay. So I'll save this name, simulation name. I'll give this name as a transient analysis. Transient analysis. So I should give underscore. So there is no space between this when you are giving the name. Now I'm giving the underscore. Now I'm saving this. This test bench we have done the transient analysis. Now I should draw the layout to the what? This inverter schematic. To draw the layout, you need a layout canvas. How to get the layout canvas is nothing but go to the tools. Go to the tools. Click on to SDL. Means schematic driven layout. SDL means schematic driven layout. You are viewing this as a layout. Click on to OK. So this is what your layout canvas, where you are going to draw the layout to this. Okay. So I'm going to generate the layouts from the tool. So this is a PMAS. I will generate the PMAS. Pick and place. These are the PMAS. So what is the width I'm working here is nothing but the width is 0.1 micrometer and length of this is nothing but 28 nanometer. Means 30 nanometer. Length is slightly higher than the exact. Okay. So this is a PMAS and also we can generate the NMAS. NMAS layout. So generate the NMAS layout. So and then now I should align this. To align, we'll be using some bind keys. 4 bind key I'm using. Then I should draw, connect the gate and gate, correct? So press P, take the poly and press R for rectangular shape and draw the poly. So gate and gate is connected here. Okay. And then I should connect the what? VR here. So to get the VR, you can go to press O and this is a VR. I'll be changing the left and right enclosure because I'll be getting the DRC rule. To change the left and right enclosure, you can go to the property of this VR. So the left and right of this should be, since I know this value I'm directly giving, we'll be understanding how you can calculate all these values. Minus 0.006. So this is one where I can reduce this left and right enclosure. Okay. So this metal right side I'm going to reduce to 2 and I just click on to apply. So now this is the VR to connecting contact is connecting to the metal to the VR, metal to the poly. If you want to change any angle, you can go here, change it to any angle. So this is a poly to metal contact. So after drawing the poly, So then you can draw the metal. So this is a metal. So let me use the bind key R for drawing the input. So this is the input. So this is the input. Okay. So now I should connect the what? VDD and VSS. To connect the VDD and VSS, go to the create multipath manual. So P subguarding is nothing but VSS, and N subguarding is nothing but VDD. This is a VDD. Now I should align this properly. Align here. And then to reduce the area, you properly use the VDD and VSS. Now I should connect this source to the what? VSS. Take the metal one, connect the source. This source is connecting to the VDD. This is a VDD, and similarly, this source is connecting to the VSS. This is a VSS connection. So then I should connect the what? Drain and drain. For that I will be using metal 2. So let us draw the metal 2 here. This is a metal 2. So here I should draw the metal 1 to connecting the metal 1 to the metal 2. Here I am going to take the metal 1. This is a metal 1. And here also I should connect the metal 1. So this is what drain and drain connection. So if I'm using different metals connection, I should place the via. What via is nothing but metal 1 to metal 2 via. So this is 1 to via. I'll connect the metal 1 to metal 2 via. Here also I'll connect the metal 1 to metal via. So all these rules, what are the vias you can use. So that we will discuss okay later. So I'm just showing that how you can plan to draw the layout for the inverter. And then this and this should be aligned. And to area constraint, you can reduce the VSS. Here also you can reduce the VSS. Yeah. So this is what the inverter in 28 nm. So after drawing the layout of this, then you should do what? Physical verification. Like you should see the what? Design rules checks, DRC and LVS. To check the LVS, place the what? Pins here. So I should label the pins. How to label the pins is nothing but press P and function F3. Press L and function F3. So here I'm going to label this as an input. I can give the font size. I'm labeling this as to the metal one. So this should be metal one text. Metal one text. You place the input. This is a pin representation. This is an input pin. Similarly, I should do what? Output pin. I'll give the output. So this is a metal 2. I'll be using the metal 2 text. So hide this and then you can rotate and keep it here. Out. So then I should label the VDD and VSS. Label function F3. So then this is VDD. I'm using capital case VDD. This should be metal 1 text, M1 text, and place in the VDD. This is a VDD, and then similarly you can VSS, correct? Function F3. Sorry. Get this option. This is nothing but VSS. VSS. Keep it here. So now we are done with the layout and then pin connections. Then you can save. To do DRC and LVS checks to this, go to the verification. So there is an option called as DRC. Here you can run setup and run. Now it will check the DRC checks. You can see what is the tool we are using is nothing but. So this Calibre and Arclas is a third-party apps to check the DRC and LVS. Synopsys tool will support for third-party apps also. From the Synopsys, what is the tool we are using for DRC and LVS is nothing but IC validator. Click on the IC validator, and then where you should set the run set file. This is what the run set file we have done. And this is a map file is required. We are mapping this file. Mapping file is added. Then you can click on to OK. So once you click on to OK, it will start running the DRC. If any rules violations done as per the 28 it will print the error here. So now you should check what are the DRC rules are there. Some DRC rules are there. It is saying that NVEL minimum width is not 0.45. So this is NVEL we are using in the schema layout. So this is what NVEL region. So this NVEL region is not area format 0.45. This is a one DRC violation. So like this, you can see other violations are there. Few violations we should address. So diffusion minimum area it should saying that 0.02 and metal area. Okay. So NVEL area. So these are the DRC rules where you should address. You should make this DRC rule as clean. So I was getting error like uh, errors, right? We should clean all these DRC rules. So after cleaning all these DRC rules, then you should do what LVS. To do LVS, you can use the same tool called IC validator. Click on to LVS, then check the what? I use the IC validator and check the LVS. So if I run the LVS, obviously I have some DRC violations. So LVS rules also I'll get the error. Now LVS is running. Once LVS run, it will show that LVS error here. It is saying that LVS is what? File. So where you can see all the errors and then you should address the LVS errors. There are some errors are there mismatch. In schematic I have given as pin name as V in, V out and VSS. But in layout I have given is capital case. But this should match. So nets is net with different name is not matching, and then you can see that saying that this is VSS. In layout we are using in the layout schematic I'm using small VSS, layout we are using capital VSS. So it will do schematic versus layout checks. Okay, and some net is not connecting, unmatched nets are there where you should address this one. Okay, here almost all LVS errors you are getting is what naming is not correct. Okay, so this is how you can do LVS checks. So after doing the LVS checks, then you can do what? Parasitic extraction that you can do by using LPE. This is what LPE extraction. Layer parasitic extraction. So you can see that what is the tool we are using for this is nothing but star RC tool. Click on to star RC. So to extracting LPE, where you should clean the DRC and LVS. Anyway, in our design, few DRC rules are there, DRC errors are there, and then LVS are there. After cleaning those two, then you can go for LP extraction. So now extraction is, even though it is done, but you won't get the correct output because pins are not matching. Okay. So this is how you can extracting the LPE. So once you extract the LPE, you can see that where parasitic resistance and capacitance you can see in the design. And you can go to, no, this parasitic extraction is not done. The reason is that where my LVS is not clean. You should get that parasitic, uh, your LVS and DRC should be clean. I'll be showing you from other design. Let us go to this design. I am not extracting the parasitics. So okay, if you see this one, so where you are extracting the parasitic, you can see that this is what parasitic resistance and capacitance is found. So after extracting these parasitics, then you can go for what? Force layout simulation, where you can perform the layout, force layout simulation, comparing the result of your force layout. Yeah, once you do the force layout simulation, you can meet the specifications from your pre-layout simulation to the forced layout simulation. So you should try to match the results. So this is how you can start with designing uh, digital uh, gates or digital circuits using standard cells and analog blocks and analog mixed motor blocks. So these are the tools you are going to encounter during the layout drawing. See, for the demonstration, I am taking very simple, means inverter. We'll be dealing with the op amps, current mirror circuits, differential pair circuits. Then how you can design op amps using charge pump, those circuits, how you can plan to draw the layout, some layout concept. Those things will be detailedly discussing in the courses. So this is regarding about today's demo session. So with this, I'll be stopping here. Any questions from your side? You can please go ahead. Yes, online students, any question from your side? You can please go ahead. Yes, Sandhya, any questions from your side? Can you please?
No, sir, I'll go through these recordings once.
Okay. Yeah, so with this, I'll stop the demo session here. Okay. Thank you, one and all.